Hello, welcome again in this video lecture series for ACD. So let us start with a kind of revision what we had in last lecture. So we had this pi module of a transistor. We started with higher frequency response, and then when we started with higher frequency response, what we have seen is some internal capacitances and resistors inside the component. Even we had a discussion about base spreading resistor RB-B, is it? And considering all of those, we have concluded with a pi module of a transistor. It is high frequency pi module of a transistor. Right? So that module I'm going to use to analyze the transistor at higher frequencies. Right? See what is the change in lower module or low frequency H module and high frequency pi module. The change is, in case of higher frequency pi module, we have considered internal components of a transistor, some internal resistors and internal capacitors. So whatever we have discovered, the resistors and components we have connected in a circuit, in a module, and then only one extra thing that we have connected, that is GM. Look at this, GM is the only new thing. What is that GM? Basically it is a transconductance. It is a transconductance. We have written equation for GM as GM is equals to what? It is IC, that is output current, divided by input voltage. Now what is input voltage? VB dash E. So that's why we have concluded IC is equals to GM multiplied by VB dash E. Now and that collector current, that is output current, we have shown in the hybrid this pi module of a transistor. What I can say is a pi structure. Now what is that GM? Transconductance basically, or how can I write equation for the transistor? This GM, it is written that IC divided by 26. Right. Now again the question will be, what is that 26? Right. It is a thermal voltage. Actually it is defined as a thermal voltage. Let me check whether we are having any reference of that thermal voltage. Okay, let me write that first. The IC that I have written in numerator, it must be in milliamperes. Is it? Actually it is IC which is in milliamperes divided by the thermal voltage VT in millivolt. That's what the actual equation. So IC divided by VT is nothing but your GM, that is a transconductance. Is it? Where I can write VT is what? Thermal voltage. Is it? The room temperature divided by 11,600, sorry 6,000. Is it? That's what the actual equation. See now again the new term T, where T is what? Where T is a room temperature. What I can write? T is room temperature. Now how much room temperature is? Generally it is 27 degree, or if I want to define in Kelvin, then standard value is 300 K. Is it? So if I put T is equals to 300 K in the equation of VT, that is 300 K or 27 degree divided by this particular value, then value of VT becomes 26 milli, that is 26 millivolt. Is it? So I'm telling you because questions should not be there from where we are getting this VT and all. Is it? So basically it is a transconductance which is IC divided by VT, that is 26 clearly. So henceforth whenever you want to calculate the transconductance, and if you know this collector current, so divide the collector current with 26, you will get transconductance. Yes, that's what the only thing. Now apart from that, so now I think all things are clear about this high frequency pi module of a transistor. Is that so? As if now we have concluded with this pi model, let us use that pi model somewhere. Is that so? Now where to use? To use that pi model, or by using that pi model at higher frequencies, we will calculate voltage gain. Voltage gain of that pi module. Is it that pi module is nothing but a BJT? It is nothing but a transistor at higher frequencies. Is it not? So this is what? This is a transistor at higher frequencies. So if this is the transistor at higher frequencies, then let me check whether I can. Yes, I can copy that, and we will use the same scenario. We will use the same pi module, and we will calculate its voltage gain. Is it? Now I'll answer why we are calculating only voltage gain. Is it? There are different ways to calculate voltage gain. Is it? What are those? I'll tell you. First, let me have this. Okay, load resistor RL is already connected, and somewhere here I'm taking voltage, that is output voltage across the load resistor. Is it? Now, what is my aim? My aim is to calculate voltage gain for that pi module. Is it? And the title that is mentioned in your syllabus is CE, that is common emitter voltage gain, common emitter voltage gain with load resistor, RL. Yes, actually this is the exact line which is mentioned in your syllabus. What is the meaning of that? It has a meaning that we have to calculate voltage gain. Is it? We have to calculate voltage gain of a CE amplifier at higher frequency using pi module, or using what I can say by using load resistor, or using pi module with load resistor RL. Yes, that is the actual meaning. Is it? The upper line that I have written, which is exactly mentioned in your syllabus. But what is the meaning? The meaning is we have to calculate the voltage gain of a CE amplifier at higher frequencies using pi module with load resistor. So this is what pi module with load resistor. See, I have connected load resistor. Now as I am going to consider load resistor, this dotted line should not be there. Let me draw it as a solid line. So considered load resistor. So now this is a pi module with load resistor. Yes, this thing we have satisfied. Is it? And now the circuit is what? CE, common emitter amplifier at higher frequencies. Yes, this circuit is a common emitter amplifier at higher frequencies. So this is what common emitter amplifier pi module at higher frequencies with consideration of load resistor. That's what the actual circuit is. Now my job is to calculate voltage gain. Is it? See, I have connected load resistor at the output. It means I am taking output voltage across the load. Is it? So that's what output voltage, and input voltage part is VB dash E. Let us calculate the voltage gain. Is it? Now look at this voltage gain. We can use our traditional notation, that is AV. But see, we have used this AV, that is voltage gain. This notation we have used for lower frequencies. Is it not? For lower frequencies in hybrid module, we have seen that AV was mentioned everywhere as a voltage gain. Is that? So that's why now we are in higher frequency module. So let us change the notation. Is that? Let's use the different notation. Let me use the letter K for the voltage gain. Is it? Now what is that K? K is voltage gain of above circuit. That is voltage gain of above circuit. This is what my K. Now what is voltage gain of above circuit? That is K. What is the value of K? Obviously it is output voltage divided by input voltage. Is it? Now in above circuit, what is output voltage? So output voltage is a voltage across load resistor, or what I can say, output voltage is Okay, let me use this pen. This is nothing but your output voltage. That if I want to consider only transistor, then output voltage means VCE. That I am writing in small letters VCE. That so output voltage is nothing but VCE divided by VB dash E. Collector to emitter voltage is nothing but my output voltage, and base to emitter voltage is what my input voltage. So ratio of output voltage to the input voltage is nothing but my voltage gain. Is that? So VCE divided by VBE, that's what I'm writing here. But see, this output voltage, look at this, the output current, that is IC is what? IC is output current. And how we have mentioned that output current? The output current is GM multiplied by VB dash E. Yes, that's what we are showing. GM VB dash E. Look at this output current source, GM VB dash E. This I am talking about. So GM VB dash E is the output current that I am showing. Right? And I have connected load resistor also. So IL is also an output current. See, GM VB dash E, that is nothing but your IC. IC is the output current. Now I have connected load resistor, so IL must be the output current. So what is IL? IL is current flowing through that load resistor RL. Is that? So let me write it here. It is IL. Is that? So as two output currents are there, it means we can write IC must be equals to IL. That is, they must be in same, or they must be of same magnitude but opposite in phase. Or I can write IL is equals to minus IC. That is, you can write IL is equals to minus GM VB dash E, because of value of IC is GM VB dash E. Yes, I can write that. Agreed. Now, this equation I have written, IL is equals to minus GM VB dash E, but output voltage, see, this is all about output current. Output voltage VCE, see, everything is in small letters that I am writing, is nothing but what? The current flowing through the load resistor multiplied the value of load resistor. Yes, see, I am writing output voltage. Look at this. This is what output voltage. So this output voltage is nothing but VC that I have assumed. But what is that VC? Load current multiplied by load resistor. Isn't it? Output voltage means what? Output current multiplied by output resistor. Yes, it is completely valid. But now, what I am going to write is value of IL is what? GM VB dash E. So let me put the value of IL here. So it must be minus GM VB dash E multiplied by value of load resistor RL. Is it? This is nothing but your output voltage VCE. Is that? Let me rearrange that. VCE divided by VB dash E equals to now minus GM multiplied by RL. What is this VCE divided by VB dash E? This indicates the voltage gain K. So I must write K is equals to minus GM multiplied by load resistor RL. Yes. Yes, this is what the final conclusion. Minus GM multiplied by RL is the voltage gain. Voltage gain with load resistor. Voltage gain with load resistor RL. Yes, we have proved. That's what the intention, that's what the purpose, that's what the motto of the analysis. What is the motto of analysis? To get the voltage gain when load resistor is present. See, this is what the voltage gain K when load resistor is present. Is it? Now, apart from that, see, one thing we have proved is that when load resistor is there, now what will happen if I remove that load resistor, or what will happen if I replace that load resistor with short circuit? Is that? Let me do that. And for that again I need to copy the same thing. Sorry. Here's the thing. So let me copy that full diagram again. Let me copy it. Now what we have decided? We have decided to remove that load resistor. Is it? Or instead, let me replace the load resistor with a short circuit. Is it? Now what I am doing? I will calculate the gain. Is it? See, I am not mentioning whether I am going to calculate voltage gain or current gain. I am just saying again to calculate gain by replacing the load resistor with a short circuit. Is it? So the title that I have mentioned in your syllabus is CE short circuit. Now what should be here? CE short circuit, current gain or voltage gain? When load resistor is there, there is a voltage across load resistor. Yes, when you connect load resistor, voltage is developed across the load resistor. So output voltage is present when RL is there. So if you replace this RL with a short circuit, what will be the value of output voltage? It will be 0, because voltage across short circuit will be always 0. Is it? So as output voltage is 0, that is there is no output voltage, then what's the point to calculate voltage gain? अगर आउटपुट वोल्टेज ही प्रेजेंट नहीं है, so why to calculate voltage gain? There is no use, there is no point to calculate voltage gain. So that's why when you replace the load resistor with a short circuit, you must calculate current gain. Look at this. So this is what actual title that I have written, CE short circuit current gain. So what is the meaning? The meaning is current gain of a CE amplifier at higher frequencies. Is it? When load is short circuited. Actually there is no need to write that when load is short circuited, because when you short circuit the load resistor, then only it is possible for us to calculate the current gain. Otherwise it is not possible, is it not? Now let us start with the procedure. What is the aim? Aim is to calculate current gain. Is it? Now what do you mean by that current gain? At lower frequencies, current gain is nothing but a HFE. See, this is a transistor. Is it? This is a transistor at higher frequencies. Even I have not biased that transistor. See, anywhere in the circuit RS or this R1, R2, RE is there? No, because now we are at the higher frequencies. So as if we are at the higher frequencies, those lumped components will never come in picture. At higher frequencies, only distributed components which are not visible by open eye, is it? Which are not connected by us, but those are present inside the transistor, they will only come in picture. Is it? And one extra thing that I have connected is load resistor, just to calculate voltage gain. Now I am removing that load resistor, I am replacing the load resistor with a short circuit, and then I am calculating its current gain. Is it? Now let us start with, first thing is to replace this load resistor with a short circuit, is it not? So let me remove this load resistor RL. Yes, see, I have removed that load resistor RL. Now what to do with this? Replace it with a short circuit. Look at this. See, I have replaced it with a short circuit. So obviously when RL is replaced with the short circuit, the value of output voltage will become 0 automatically. That can be neglected. It will vanish it out. Right? Now, I think that diagram is okay. Let us start with whatever we have. Right. So, before starting with anything, let me calculate one parameter. What is that one parameter? The parameter which is related to current gain but at the lower frequency. Is it? That is at lower frequency. What is the current gain? At lower frequency, current gain is HFE. Is it? That's what. Now, in the opposite circuit, that is circuit that I have drawn at higher frequencies. So, at higher frequencies, what is the equation for VB dash E? Just check it out. VB dash E is what? That is base to emitter voltage. This voltage is nothing but the voltage available across this resistor. The resistor is RB dash E. Look at this, RB dash E multiplied by current flowing through the resistor. Now, what is the current flowing through that RB dash E? Obviously, it is a base current. Is that? So, VB dash E is nothing but RB dash E multiplied by IB. Is that? So, if I write it as an equation number 1, then now this is about the input voltage. Right? Now output current, that is IC, already we have this, it is GM multiplied by E. Right? Now this VB dash E value, if I replace here in the equation of IC, then it will be GM multiplied by IB multiplied by V dash E. Is it? Now this IC, see, we are calculating everything at higher frequencies. Now let me rearrange this. This IB will go in this side, then IC divided by IB by E. Now what it shows at lower frequency, what is this? This is nothing but your HFE. So HFE, if you want to calculate at higher frequencies, it will be GM multiplied by RB dash E. Yes, that's like this. See, only one parameter, the parameters or hybrid parameters that we have used at lower frequencies. Is it? So I have derived only one parameter, HFE, but by using that pi module, you can write all equivalent equations for HFE, then HRE, HOE and HE. Yes, it is possible to write equations for all of those. Is it? All of remaining H parameters. It is possible. See how much time we spent. Only 1, 2, 3, 4. 4-line derivation is there for HFE. Like this, there will be a 4-line equation for HOE, HIE, HRE. Is it? So we can prove that. I just want to show you that it is possible that we can derive H parameters at higher frequencies. We can derive equivalent equations for H parameters. Is it? So at higher frequencies, if you multiply GM and RBE, it will give you value of HFE at lower frequencies. Is it? This product, that is GM multiplied by RB dash E, this at higher frequencies, is it? At higher frequencies will be equivalent to the HFE at lower frequencies. So that's what I wanted to show you basically, and somewhere I will use that equation GMRB dash E. Is it? Because I want to calculate the frequency, cutoff frequency instead. Is it? Now look at this. This is a value of HFE. Is it? But that was not the actual aim. The motto was different. What is the motto? Motto is to calculate short circuit current gain. See, this is also current gain, HFE, but this is not a short circuit current gain at higher frequencies. Is it? We have derived or we have calculated a lower frequency current gain equivalence. is it? But equivalence is not needed for the time being, is it? We want an exact thing. So let us proceed for the exact thing. Okay, once again I need to copy this. See, this thing I have to copy. Is it? So many times we need to use the same diagram, is it? Because it's a pi module. Everything that we are going to derive is from pi module, is it? That's what. Let us start. This is a, let's see, we have replaced this load resistor. We have replaced, yes, we started with this thing. Now when you replace load resistor with a short circuit, now let me change the color of your pen and let me show you that RB, okay, the actual name is RB dash C, while RB dash C, this RB dash C resistor, look at this, the second terminal of that RB dash E, where it is connected, the second terminal, this second terminal is now directly connected to the ground. Look at this. And even second capacitor, it seems to be directly connected to the ground, is it? So it means directly those R B dash C and R C, sorry, C B dash C, those one capacitor and one resistor get directly connected to the ground, is it? Get directly connected to the ground, and the modified circuit will become, now let me modify the circuit. That I need to remove from here, because now it is directly connected to where it is connected, it is directly connected to the ground, is it? Even this capacitor, that I need to remove, C B dash C. Now if I am removing that, where I need to connect it, I have to connect it directly to the ground. It means the resistor and the capacitor, let me put a dotted line here, or one capacitor that I have to connect here. The notation that I have to use for two capacitors, one is C B dash C, another one is C B dash E. That's what it is. Okay, it's going slow. Okay, I'll use stroke eraser. Now this is what? This is C B dash E. Now what is this? C B? One capacitor, that is C B dash E, directly connected to the ground. And what about the resistor? Look at this. One resistor has to be directly connected to the ground. What is the name of the resistor? It is R B dash C. Look at this, R B dash C. I'm showing a dotted line. Is it? Why? Because if there is a short circuit, RL is replaced by the short circuit, then that short circuit may affect on the capacitors, but I don't want to consider that, because see, I have not replaced the capacitors with its capacitive reactances, is it? So that's why now I am keeping a dotted line there. Now look at the circuit. This is a short circuit. Let me change the pen. Look at this. This is a short circuit. That short circuit is in parallel with RB dash C and RCE. Now anything or any value of resistor, when it is in parallel with the short circuit, what will be the effective resistance? Obviously, effective resistance will be short circuit. Right? Any resistor is in parallel with the short circuit will be short circuit always, is it? So that's why now this circuit can further modified as, now look at this. See what I'm drawing here. I'm just drawing RB dash E, then two capacitors, sorry, 1 and 2, two capacitors. What are the name? One is CB dash C, another one is CB dash E. Look at this, CB dash E, and this is now CB dash C, is it? And what is the remaining part? Remaining part is only a current source. What is that current source? It is only GM multiplied by VB dash E. Yes, that's what the only thing at the output side, and the load resistor which is replaced by the short circuit. This is what, even if you don't show this base spreading resistor, then also it is okay. See, I have removed this base spreading resistor RB dash B. I have removed it. Why? Because it's not necessary to consider RB dash B all the time. Why? Because that RB dash B will not the case that it will present all the time, is it? कभी कभी picture में आ जाता है वो. Why? When base depletion region spreads out, then only it will come in picture. Otherwise, commonly it is neglected, is it? कभी कभी आता है वो picture में. Why? And the reference of that already we had discussion about it, is it? So that's why what we have now at this side, we have two capacitors, one resistor, and at the output side we have nothing, is it? Now why to consider two parallel capacitors? See, when two capacitors are in parallel, for example, if this is one capacitor and this is another capacitor, can I combine it with only one capacitor with C1 plus C2? Possible. So if it is possible, then again let me modify the circuit diagram. What will be my new circuit diagram? My new circuit diagram will be only with one resistor and one capacitor is there. Look at this. It is C B dash E, okay, plus C B dash E. Equivalently, you can clearly write only C, is it? Where you can clearly write where C is equals to what? C B dash E plus C B dash C, is it? You can want to simplify this thing further. Now, what is there at the output side? At the output side, only one current source. And what is that current source? It is GM VB dash E. Replaced by the short circuit. That's what. Now, look at this. This is collector, sorry, load current. This is collector current. Even both are same in magnitude but opposite in phase. But whatever it is, we have to show it. Is it? Now you call this capacitor at the input side as C only or CB dash E plus CB dash E. It's on you complete. Now what is the value of resistor? It is R B dash E. Yes, that's what we have. Now see, as I told you so many times that in network analysis, any circuit, is it? Any circuit is converted into one resistor and one voltage source, is it? And what we call it as? We call it as a Thevenin's theorem, is it? And what's the use of Thevenin's theorem? Why? What's the purpose? Just to simplify the analysis, is it? I want to simplify the analysis, and that's why I have converted the large network into small network. A small network consists of one voltage source and one resistor. Any complicated network, convert it into resistor and voltage source. That's what it is. Like this amplifier or any CE amplifier, two stage, multi stage, whatever number of stages are there, that can be converted into RC circuit, that converted into RC circuit. That's what it is. I told you so many times that as like Thevenin's theorem, we can convert the C amplifier in single RC circuits. That's what we have. RC circuit. Do we have any RC circuit? Look at this. At the input side, this R is nothing but what? R B dash E. What is C? C is nothing but C dash E. Look at this, C B dash E plus C B dash C. That is one capacitor and one resistor. See, a large amplifier at higher frequencies reduces to RC circuit. Now, when I am saying this, that amplifier is reduced to RC circuit, then at higher frequencies, it has to show some resonant frequency or some cutoff frequency. If it is RC network, we used to call it as a cutoff frequency or resonant frequency. Is it? But that RC circuit is not RC circuit now. It is what? It is actually an amplifier. पहले क्या था वो? Amplifier था. RC circuit को हम क्या बोलते हैं? It is cutoff frequency or resonant frequency. Is it? But now resonant frequency equation तो हमें पता है for RC network it is 1 divided by 2 pi RC. Is it? But that RC circuit is nothing but my amplifier. So for amplifier, what we have? Higher frequency. So higher frequency, it will be 2 pi. What is the value of R? My R will be R B dash E. So I'll write R B dash E multiply by C. C means this I have. That is, okay, let me write it in brackets. C B dash E plus C B dash C. Look at this. This is what my cutoff frequency is. Right? So now this higher cutoff frequency we are getting because we converted a C amplifier into RC circuit. Is it? कैसे हमने convert किया? We converted the amplifier into the RC circuit by replacing RL with the short circuit. Is it? By replacing RL with the short circuit. So if you don't replace RL with the short circuit, then obviously that cannot be, or amplifier cannot be converted into RC circuit. होता नहीं है. So it means first thing is we have to convert that RL into short circuit, and then only it is possible for us. Then only it is possible for us to convert the amplifier into RC circuit. Is it? Now look at this. What happened? Oh, that laptop battery. Let me check. Okay. So are we in 7? Okay. Okay. I'm really sorry for the interruption. Okay, where we are? So if it is an RC circuit, its cutoff frequency is FR. That's what the cutoff frequency. But now this is not RC circuit. Actually, it is an amplifier. So if it is an amplifier, I must write higher cutoff frequency. Is it? Instead of FR, resonant frequency, it must be then higher cutoff frequency. Is it? So this is higher cutoff frequency. Generally, the cutoff frequency or higher cutoff frequency or lower cutoff frequency, how we define it? We define it that is or as the frequency where gain drops at minus 3 dB. That's what we do. If it is an RC circuit, the maximum gain is 0 dB. Then when it falls to minus 3 dB, so the level at which it falls to minus 3 dB, that level frequency we consider at a cutoff frequency. Is it? No. For the amplifier, when the gain falls to minus 3 dB, the level or the frequency at which gain drops to minus 3 dB is what my cutoff frequency. Maybe it is higher cutoff frequency or lower cutoff frequency. Is it? Now the question is which gain it must be. Is it? It is a voltage gain? No, it must be a current gain. Now look at this, it must be a current gain. Why current gain and why not voltage gain? See, because initially we have replaced that lower resistor with a short circuit. So when there is a short circuit, output voltage will be 0. Output voltage will be 0. So obviously output voltage divided by input voltage, 0 divided by anything. What's the value then? Is that? So there is no point in voltage gain. So the gain that I am talking about is only current gain. So it means the frequency at which current gain drops to minus 3 dB is what my higher cutoff frequency FH. Is it? The current gain means, what is that current gain? Current gain means HFE, na? Or simply it is a beta. HFE or beta is nothing but a current gain. Is it? And even we have derived equivalence of that. What is the equivalence? HFE? The value of HFE at higher frequency, it is Gm multiplied by RB dash E. Look at this, we have derived. Yes, Gm RB dash E. You remember that. Gm RBE or RB dash E. So what is that HFE? It is Gm dot RB dash E. This is the value of HFE, or this is the value of current gain. Is it? Now for the time being, we have nothing to do with what is the value of HFE. We stick to the level, that is a frequency at which current gain drops to minus 3 dB. Is it? The frequency at which current gain drops to minus 3 dB is called higher cutoff frequency. Higher cutoff frequency, and this is denoted by F beta or F HFE. Why it is F beta or HFE? Because beta and HFE shows the current gain. Is it? It shows the current gain. So that's why that frequency is called F beta or F HFE. So then this equation for FH, whatever we have written, this is not FH actually, it is F beta. It is called beta cutoff frequency. So what will be the equation of F beta? It is 1 divided by 2 pi R B dash E and the value of capacitor C B dash E C B dash C. Look at this. So this is the equation for beta cutoff frequency. It is called beta cutoff frequency. Right? Why beta cutoff frequency? Because we are in C amplifier. Look at this. Common. So if I consider common base amplifier, see, this is all about common emitter. Now if I consider common base amplifier, then at that time for common base amplifier, current gain will be, current gain is equals to alpha. It's not beta, it is alpha for common base. Is it? Then for common base amplifier, the frequency will be F alpha instead of F beta. Is it? And if you follow the same analysis, then you will find that value of F alpha will be 2 pi R B dash E multiplied by 1 HFE C B dash, sorry, okay, C B dash E, and this is the value of F alpha. And what it is called? It is called alpha cutoff frequency. It is called alpha cutoff frequency. Now look at this, beta cutoff frequency and alpha cutoff frequency. Now what are those frequency? The frequency at which current gain, a frequency at which current gain drops to minus 3 dB. Is it? The current gain of pi module C amplifier or current gain of C amplifier at higher frequencies, whatever you say. Is it? So this is all about the alpha cutoff frequency and beta cutoff frequency. But see, this is not the end. Is it? The aim is to get current gain. HFE is not the current gain. HFE is the current gain at lower frequencies. लोअर फ्रीक्वेंसी में जो करंट गेन आता है उसका एक इक्विवेलेंट छोटा सा हमने फाइंड आउट कर लिया, बट दिस इज नॉट द एंड, दिस इज नॉट द एक्चुअल कंक्लूजन. एक्चुअल कंक्लूजन इज क्वाइट डिफरेंट. हमें करना क्या है, व्हाट वी नीड टू डू, वी हैव टू कैलकुलेट इट्स actual current gain at higher frequencies. Is it actual gain or actual current gain at higher frequencies? That's what our thing is. Is it? Now let me check how much time we have spent. Around 45 minutes. So it is possible now. So let us continue with current gain. Is it? So it is AI. Let me denote it by AI. Now, what is AI? It is actually current gain. Current gain at higher frequency. The title of what we have written is what? CE short circuit current gain. CE short circuit current gain. That's what we want actually. Right. Now to process or to proceed for the CE short circuit current gain, again what we need a reference of that pi module. Obviously everything is there with reference to the pi module. So one capacitor, one resistor will be there in picture. Now what is that? This module I need to consider. So let me copy and paste the same module. Okay, yes, this is either you call this as a combination C, that is CB dash E and CB dash C, whatever it is, it's on us completely. Now the voltage, sorry, the current gain, the equation will be, okay, let me write it AI CE short circuit current gain. That's what the actual motto, that's what the actual purpose that we need to derive for. AI is equals to what? It is output current divided by input current. So output current is IL, input current is IB. It is well known. Low, let me call it as equation number 1. Is it? But value of IL, it is minus GM divided by VB dash E, that we have seen already. Is it? What is the value of IL? It is GM VB dash E. Is it? This is known. But value of VB dash E, look at this, VB dash E. Again I can write as IB multiply by, now see I am writing something new, ZB dash E. Now what is that ZB dash E? Yes, that's what the only new thing. Now look at this, let me change the pen. This ZB dash E is nothing but the parallel combination of capacitor and a resistor. Yes, this I'm calling it as ZB dash E. Is it? Isn't it? So what I must have? I must have the base current. Look at this. The base current IB, which is flowing through this ZB dash E. This is the actual voltage. Is it? The voltage that I am referring it as an VB dash E. That is input voltage. That is input voltage. So input voltage VB dash E is equals to what? The current flowing through the input resistor. What is input resistor? It is ZB dash E. Is it? Now the only new thing that I am writing in the analysis is ZB dash E. Okay, let me elaborate that also. What is that Z B dash E? Okay, let me change the pen. Yes, it is changed. Z B dash E. Okay, let me retrace it. Z B dash E. What is that Z B dash E? It is a parallel combination of R B dash E and the value of capacitor. Actually, it's a capacitors because we have two capacitors. But what is that C? C is C B dash E plus C B dash C. Okay, let me call it as equation number 3, equation number 4, equation number, it's not needed to call this as a separate equation. Now what will be the hierarchy? I want to get this AI, is it? To get this AI, first I have to calculate this, is it? It means I am going to calculate Z B dash E. When you calculate Z B dash E, put the value of Z B dash E here and then calculate V B dash E. When you calculate V B dash E, put the value of V B dash E here and calculate value of IL. When you calculate value of IL, put the value of IL in this equation of AI and finally get AI. Yes, that's what the simplest process we need to follow, is that? Now, as a first step, let us calculate this ZB dash E, right? But while calculating ZB dash E, I'm using C only. I'm not writing the complete C is equals to CB dash E and CB dash. Once if enter two values for one capacitor, again there will be a confusion, is it? Just to minimize the confusion or to avoid the confusion, let us use only C instead of ZB dash E. Sorry, let's use C in the equation of ZB dash E. So ZB dash E calculation was the first part. Let us start with ZB dash E. What is ZB dash E? To R B dash E in parallel with the capacitor C, is it? So Z B dash E will be, now let us write again R B dash E multiplied 1 divided by J omega C, is it not? See, I am not writing value of C, that is C B dash E and C B dash C, is it? Now it will be R B dash E plus 1 divided by J omega C. That's what the only thing we need to solve it. If I solve this further, then what I am getting? Value of ZB dash E, value of ZB dash E will be then RB dash E divided by RE multiply by, yes, this is J omega C multiply by RB dash E plus 1, yes, J omega C plus 1, isn't it? RB dash E multiply by J omega C plus J omega C will this will go in up direction, they will cancel each other, only R B dash E. So R B dash E divided by R B dash E J omega C plus 1 is the remaining thing, that is Z B dash E. Now that value of Z B dash E, where to keep this value of Z B dash E? Yes, that value of Z B dash E, I have to keep it in V B dash E. Yes, so let us do it. Then I will write keep this in the equation of VB dash E and calculate VB dash E. Now what is the value of or equation of VB dash E? Equation of VB dash E shows IB multiplied by ZB dash E. Then VB dash E becomes, so equation of ZBE is that I need to multiply with IB only. So VB dash E will be IB multiplied by dash E divided by, equation will remain as it is, multiplied by J omega C plus 1. This is what VB dash E. Now what to do with this VB dash E? Let me check. We'll follow the same scenario as we have discussed. Come on, load it. It is taking quite time. Now VB dash E part we have finished. Put this value of VB dash E in the equation of IL. So what is the value of IL? Value, or keep VB dash in the equation of IL and calculate IL. Okay, let me write what is IL. IL is equals to minus GM divide multiply by VB dash E. So it will be minus GM multiply by R B dash E. I'm putting value of VB dash. That's what it is. R B dash plus 1. And this is value of IL. Is it? Now, after we conclude with the value of IL, what will be the next step? Or what was the next step we have decided? It's calculation for gain, AI. So, what is that AI? AI is nothing but IL divided by IB. It means now this IL, whatever we are getting, we have to divide it by IB. Right? Now, look at this. Minus GM R B dash E. Okay, we are missing IB here in the equation. Okay, IB must be there. Right? Now, AI is equals to AI is equals to what? IL divided by IB. So divide the value of IL and get the value of AI then. Now with the AI, AI will be this equation, is it, divide by IB. So finally what you are getting, it is minus GM multiply by RB dash E. IB will get cancelled. Then RB dash E J omega C plus 1. Yes, this is what the equation AI. But see, this is not the final equation. This is not the final equation. We are still in the imaginary part. Still in imaginary part. So what is the imaginary part? Imaginary part is obviously j omega c. And this is that. Yes. Let me put the value of omega in the above equation. Is that? Okay, let me rewrite the equation again. It is AI is equals to minus GM as it is R B dash E, that has to be as it is. So what? 1 plus, it is 1 plus J R dash omega, that is 2 pi f, and a capacitor C will be as it is. See what I left with? J, yes, J is there, RB dash E is there. Then omega is equals to 2 pi f. Yes, I am keeping omega is equals to 2 pi f. Then C it is, yes, C is this, plus 1 plus, yes, everything is there in my equation of AI. Right? So now here also I can put the value of C. Yes, I can do that. Okay, let's do it then. Now put value of C of capacitor C. What is the value of capacitor C? C is equal to C B dash E C B dash C. That's what it is. If you want to, you can put the value of C here itself in the above equation. Okay, let us rewrite. Minus M R B dash divided by 1 plus J R E 2 pi f, and now I am keeping value of C, that is C B dash E plus C B dash C. That's what it is. Yes, am I done with? Yes, I'm done with. And this is value of AI finally that I'm getting. Now can you observe that equation? Let me use the pen. Hmm. Let me write here. What is the value of f? Okay, I want a dark pen actually. Okay, let it be f beta. What is the equation of f beta? No, it will take a lot of time to copy that. What is the value of f beta? It is 1 divided by, it is 1 divided by 2 pi r b dash e plus b dash e. Yes, that's what f beta we have derived already. Just check it out. Can you find this f beta in this equation? Okay, let me scroll it down. It is 1 divided by r b dash e. 2 pi is also there. Then look at this, c b dash e plus c b dash c. See, everything is there. It means now f beta is there in the equation of AI. So let me rearrange it, and rearrangement will be by gm multiplied by e divided by 1 plus, still I am keeping a value of j as it is. Now it will be divided by f beta. Let's check whether this arrangement is okay. Let's check f beta. See, I'm just putting value of f beta here in above equation. Yes, I can find f beta. 1 divided by 2 pi r b dash e, everything is there. C b dash e plus e b dash e, yes, it is also there. So let me write it in the form of f beta. Is it? So this is the actual equation of AI. Is it? Now this AI, that is IL divided by IB. Is it? In this equation, now what is it? Is GM multiplied by RB dash. What is that? It shows HFE. So for purely optional thing, that you can rewrite the equation as divided by 1 plus J F divided by F beta, and this is the value of short circuit current gain at frequencies. This is short circuit current gain at higher frequencies. Yes, this is what, this is the actual thing for what we are hunting from last 1 hour, is it? But meanwhile in the process, see, what was the aim? The aim is to get short circuit current gain, but in the process what we have covered, see, we have calculated the equation of HF is frequency component, but we calculated its equivalent value, that is GM RB dash E, is it? Then after HFE we have seen one term F beta, that is beta cutoff frequency. We have seen alpha cutoff frequency. So at the descriptive exam, one can ask you to derive only F beta, one can ask you to derive only F alpha, or they may ask you to derive equation of AI. Yes, they can. The value of short circuit current gain, is it? So I think it is more than 1 hour, and whatever we have planned with, we are done with. Then F beta, F alpha, HFE, AI, everything is covered in this lecture. So probably that much is okay for that higher frequencies. The next part is, I said, still we are missing that FT. So in next lecture we will cover that. I'll tell you in detail what is that FT actually. Part of a data sheet. It's a part of data sheet. So we'll cover that and then we'll discuss how to use that FT from the data sheet. Alright. So we'll start it in the next lecture. Thank you.